Wow. We ready to get started? Because at first I wasn't sure anybody was showing up. The first time I walked in a room that was completely empty. I wasn't even that early, so I don't know.
There was free candy out there. So
is that what
probably got
the deal? Yeah. I know, I passed up, and it's not like me because I love candy probably more than everybody. I do. I know the older you get, I love candy, but I love it. All right, where are we at here? We're going to get started. I want to start by, I don't know. I want to get started. I'll finish in these a couple things by reviewing a little bit from Monday. Okay? I gave you two. Are they both here? Are they both here? Okay. Oh, real quick, you obviously know. Oh, you're on the book. Just want to refresh your memory. There is a quiz today. I mean Monday. See if anybody's here. Okay. Well, matter of fact, let's take advantage of this moment and have some participation. I'm going to ask you some questions from the last lecture because these simple, easy rules are what's going to make you breeze through the Chapter 6 questions and focus on the Chapter 4. Transportation model, assignment model, transshipment model. Every one of these models have nodes, and every one of these, the nodes represent what? Constraints, you got it. Every one of these have arcs, and the arcs represent what? Very good. All right. If we were looking at a transportation model, and we were writing the constraint for the left-hand side supply nodes, most of the time it's either what? Greater than, equal, less than equal, or equal? The supply nodes, Mike, I appreciate you jumping in.
Less than equal.
The effort, I appreciate the effort as much as the answer. Less than equal, because the supply doesn't have to send it all on. They could have more than what they were possibly. In most cases, there are rare circumstances where it might be equal, but in most cases you can count on less than equal. The customers on every one of these, the nodes that represent the right-hand side customers, those constraints are all less than equal, equal, or greater than equal. Equal. Got it. Right. There's a very rare situation it would be different than equal, so you can pretty much count on that one too. Let me make sure I got everything. Oh, all of these on the arcs are represented with numbers that represent costs or profit or whatever, or days or time. And all of those numbers are used within the constraints, true or false? They're used where? Very good, guys. All right. I mean, that's how simple these rules are. You have those down, you're going to fly through Chapter 6 questions. Now, that was preparing you for these last two. Because these last two each have their own little differences compared to the other three that I want to make sure you understand and you have written down somewhere. So if you can start with some of the obviouses, here's something that's obvious with all five of them. It's going to be consistent. The nodes are constrained. All right, we can say that for all five. And as soon as you look at a problem, if your memory goes blank, at least say, well, the nodes are constraints and start from there. Because you know that's right. The arcs are variable. All variables, all five of them, these two also. The arcs are variables. The difference is, when you get to shortest route, this has a different rule about the arcs being variables compared to the other ones. This is what's weird. See all the lines here. I'm not talking about the ones coming out of the smallest numbered node, which we call the beginning. And I'm not talking about the arcs that are coming out of the largest numbered node, which we call the end. But all of these arcs between the middle nodes are actually two variables in shortest route. Let me repeat that, because you've got to know that when you see a shortest route problem. All of these arcs going between middle nodes, 3 to 5, 5 to 4, 4 to 3, 2 to 5, whatever else is going between middle nodes, represent two variables, not one, like all the other problems. unless there's a specific arrow on the arc. You have to assume they go both ways and they represent two variables unless you visually see an arrow on the arc. That's trying to tell you that's one of the rarest cases where it's a one-way. Shortest route is used a lot in logistics. Remember we were talking about logistics. Logistics isn't just about planning what's put in the truck, what the truck is going to pick up on the way back and things like that. But a big part is also the logistic person is planning the whole route. On the way out from leaving our organization all the way on the way back, the exact route that will keep costs as low as possible, including the cost of the truck itself that we own as a company. The gas, the wear and tear, all of it. And so this is part of the program for logistics occupations. They have to use software that does exactly what we're about to learn to figure out the best route. These middle arcs represent both ways, and that's why they're two variables. For example, x34 is if the route goes from this location to this location. But x43 represents the other direction, which could happen depending on, there's so many different ways it could go before it gets here. For example, I want to put one out there. It could go from 1 to 3, 3 to 4, 4 to 5, 5 to 2, then 2 to 6. If that's the cheapest way to go, that will be the plan. Now, for shortest route, this is another one you got to write down that's different. All the arcs coming out of the beginning are only one way. They never go back to the beginning. They're one way out from the beginning. Now, right under that, write down all the arcs that are going to the very last node, which is the highest number node, are only one way. They only go in. Go ahead. Okay. Remember, I just got to say all the arcs in the middle go both ways. The arcs at the beginning, if they're touching that first node, they're one way only. No arrows or nothing. They're one way. They're coming out of the beginning. You never go back to the beginning. And the ones at the end that are touching the end are one way only. Once you get to the end, you're done. There's no way of going back to another town or another location. One way. All right. All right. Here's something that's very different about shortest route compared to the others, is that all of these middle nodes, but this isn't different, this is similar. Remember transshipment. In the middle nodes, what is it we got to do when we write constraints on the middle nodes on transshipment? Other than making them equal to 0, what else do we have to do? Some are minus and some are plus. Some are going into the middle nodes, some going out. That logic is exactly the same logic for the middle nodes. There's always positive and negative variables, and they all equal 0, just like transshipment. But here's what's weird. All the ones coming out of the beginning, you're writing them as positive variables no matter if you made the ones going in negative over here. So let me say that again. When you write the constraint for the beginning node for shortest route, all variables involved are positive variables, not negative, no matter what your instinct said. And that exact statement is true again for the ending node constraint. If your instincts are telling you to make these all negative because they're going into a node, don't allow that to happen. All variables at the constraint for the end are all positive, no negative. No matter, so you got positive at the beginning, and you got positive at the end, no matter what. But in the middle nodes, all of those constraints should have both positive and negative, and they're all equal to 0. I'm going to add one more thing, Mike. Ready? At the beginning, this constraint is always equal to 1. At the end, that constraint is always equal to 1. And all the middle constraint nodes are always equal to 0. Now,
what if there are only 3
nodes?
Yeah.
I've never seen one with only 3 nodes, but the ones out coming out of the beginning would be positive. The constraint for the ending node would be all the variables would be positive, and that middle node would have both positive and negative, depending on which way you want to put So the rule still stays the same. Anybody want to repeat any of those little rules? Because if you have those down, it will make the shortest route problem real easy. All right, you ready? There's usually numbers on the arch. We have letters here because it's part of the story. But the numbers on the arch represent something, and those numbers are only in the objective function, just like the previous three models you've learned. Let me say that again. Just like the previous three models, the numbers, which might represent cost, for example, are only in the objective function, just like the previous three. We're about to head to the fifth one after this, though, where that rule is thrown out the window. The numbers are not part of the objective function at all. And that's the only one of the five where the numbers are not part of the objective function. It's called max flow, maximum flow, the long name, max flow is the name. Okay? You got it? Let's go to this example. Your job is to get our employee to this conference in Paducah from Lewisburg at the least expensive way possible. And when you're calculating the route, you've got to decide whether this employee's taking a bus, a train, a taxi, chauffeur-driven limousine, whatever the options are. And you've got to take into consideration that during travel time, the whole trip, we have to pay her the $15 an hour pay that she's getting paid also. So you got to take that as part of the cost. There's the cost of the ticket, whatever the form of transportation is. There's the cost of her time. And your objective is to get that cost, to get it from the beginning to the end at the lowest as possible. So you're given this information, which is every possible form of transportation to every possible hub between Lewisburg and Paducah or whatever, I can't remember the name of it already. In between, in the forms of transportation that would get you there, but which one's the best that would get you there. And what I want you to notice about this is the amount of time and the cost of the tickets here. But that's not what you would put in the shortest route. In the shortest route, you've got to put the total cost for every possible route. So you've got to take this time and multiply it times $15 an hour and add it to the cost of the ticket before you can put all that cost on the line. And that's what this is. There's the time it now costs, times $15 an hour. There's the ticket. Here's the total cost. If we redrew that shortest route, these are the numbers that would be on the lines. All right? All right, so now, how do you then solve this problem? And you've got to remember, you could probably stare at this long enough and that long enough. You might be able, I would say if you have enough time, everybody here could get the optimal solution and save the company the most money. It's not about taking hours to do it, or a half hour, or days. It's about getting this done in minutes. And that's why you take something like this and you turn it into a linear programming problem that you got to solve. And you set it up the first time if you actually were really doing this with software, and you don't ever have to keep redoing everything. You just have to keep re-entering different numbers. How it's done, let's start with this node right here. And I gave you the rules, so you tell me what's the right-hand side of that constraint right there? Equals 1. Just look down, it says, every constraint that represents the first node of the beginning is always the right-hand side equal to 1. Then the left-hand side is going to have how many variables? How many variables on the left-hand side of this constraint for node 1? 5, because the rule is, on all of these, is however many arcs are touching the node that you're writing this for is the number of variables that got to be on the left side. So there's going to be 5 variables. Now, are these negative or positive? Positive, because if you look down, one of the rules said, at the beginning and end, the variables are all positive. On shortest route only, max flow, different story. Shortest route, beginning and end, positive. Here we go. x12 plus, I gotta look, x13 plus, is that one going all the way to 5? x15 plus 16, wow. x16 plus x14. All I did was look at the arcs and where they went to, x13, x15, x12. And and I just wrote the constraint for the first node. I mean, it's that easy. Okay, let's do constraint 2. Let's start with the right-hand side. What is the right-hand side on that one? Equals 0. Thank you for looking down and refreshing the rules there. It's that easy. It's representing going from our beginning to that possible location on this form of transportation. We then could go from there on this form of transportation or that one. This could take us right to the end. I'm going to assume that's probably pretty expensive, and I'm going to guess it's probably a plane. Not that the distances have anything to do on these lines to the actuality. But, or we could go to 5, which then could take us to 3 or 4. We could take us to 6 or 4. We have all these different routes. But my question for you is, how many variables will be in the constraint for node 2? 3, 4, 5, 6, 7. Who knows? You ready? Who knows? One going in that can't go back represents one variable all by itself. 2 going to 5 is a variable, but 5 could go back to 2, so now I'm at 3 variables. 2 could go to 6, but can't go back, so now I'm at 4 variables. I don't see any others. The answer is 4. You see the logic I went through to figure out how many though? I'm assuming every one of these arcs are going to be two-way, unless as I look at it, I go, oh, it's going to the end, or it's coming from the beginning. In that case, it's a one-way. One was coming from the beginning, that's when I knew it was one way. One's going to the end, that's how I knew it was one way. And one was going to a node that was not to be in the end, so I went back and counted that one too. So to put this in writing, same thing I just did. x12 plus x25 plus x52 plus x26 equals 0. That easy. It's so easy that somebody's volunteering to talk me through number 3 loudly and confidently right now. Matt, what'd you say? What, Matt? I'm sorry, I couldn't hear you. You want to go for it? Yeah. You sure? Yeah. You ready? Yeah. Let's start me out with the right-hand side. This is number 3. You realize that, right? Yeah. Okay, let's do it. What's the right-hand side?
Okay, I'm looking at my notes.
Of any center node for short shrub, exactly. What 0 node?
Equal to 0.
Thank you. Equals 0. Okay, let's stare at it. I don't even want you to tell me how many. I want you to talk me through each one, and I'll write them as you tell me.
So
give me the, I know there's going to be a lot, so I gotta make sure there's enough room. X what?
X 1 3.
1 3, I'll take it. X.
3 5.
I'll take it. 3 5 plus X.
5 3.
We gotta look at 5 3. That sounds good. Plus X.
3 4.
3 4. Nice. Plus X.
4 3.
Very good. Plus X.
3 6.
3 6. Is that it?
I think that's it.
Anybody else? Oh, I thought Kid was jumping in. Is that it? Anybody want to confirm it? There is no way to give him support.
I'll confirm.
I
You
have
will?
a question.
You will? Ray, go.
I'm kind of cheating on the slides right now, but the slides say that there should be negative and positive.
Oh, almost forgot. Thank you. God, my mind is so trying to get through you guys, I forgot about this part. All right, where's our middle nodes? This one and this one, the 2 I did wrong. You ready? We gotta decide whether we're making the ones going in positive or the ones going out positive, and then we gotta do the opposite. Which way are we going? Ones going in should be what?
Negative.
Want to go negative? Okay. All those going into the node we were writing this for, you've got to switch to negative. Let's start with node 2. So that'd be where 2 is the second number. Going into 2, we're making negative. So I got x12, that's easy, negative. That's 2 5, I'll leave them positive. Here's 5 going into 2, negative. 2 6, we're leaving. There's that one. Collect? You ready? I want you to help me with this other one. Which ones are negative? Hang in there with me. The one's going into 3. Oh, she does not want to do this on Thursday here. Someone else volunteer. She wants someone else. Amanda? Anybody? Somebody. Good. So, the ones going into 3, we have to make negative. Help me out.
1 to 3.
1 to 3.
4 to 3.
4 to 3.
5 to
5 3. Is that it? Thank you. Thank you, thank you. All right. Let's do one more. I'm going to do 5. Just correct me if I make a mistake. Are you ready? Now you're putting the right-hand side on. Jumping right in. We're making the ones going into a node negative, so I'm going to go. Wait, Colette, you want to do it? You gave me that look. You did, I swear. Okay, all right, okay. Here we go, the ones going into 5, I'm going to make negative x, negative x 2, 5. I'm going to try to find another one goes into 5. Oh, negative x 1, 5. What else goes into 5? Oh, negative x 3, 5. Hang on, is that it? 2, 5, 1, 5, 3, oh, 4, 5. Does anybody help me? Minus x 4, 5. And I think that's all going into 5. And now the rest are heading out. You guys agree so far? Okay, heading out for 5. I got plus x 5, 2. Plus x, I heard someone, 5 what? 3, thank you. Plus x 5, 4, thank you. Plus x 5, that must be the end. Is that right? 1, 2, 3, 1, 2, 3, 4 going out, 1, 2, 3, 4 going in. Yeah. Yeah, there they are. Does everybody get the idea how easy this is though? Everybody okay? Let's do the objective function so we can go on to max flow because that was a little harder than this. You ready? Man, don't be scared. You ready? Max flow, or the objective function, somebody's got to have the slide open and have the total cost for each of these letters. I'm just going to start out with A. So I'm going to go max or min? Min, because these are costs. That's right. Min. X 1, 2 should have what number in front of it?
80.
I'm sorry?
80.
Thank you. Plus x 1, 3 should have what number in front?
40.
40, x 1, 3. X 1, 4 should have what number?
80.
80, x 1, 4. Plus 2, 5. What number? Oh, I'm sorry, that's letter F.
5 is
60. Okay, now watch this. Plus x 5, 2. What number should be in front of that?
60.
Same exact number. It's the same route, it's just going either one way or the other. So the same number. Now I want to make sure you guys are getting this. Someone tell me, what's H amount? What's the amount for H, please? 30? Someone say it. 30?
30.
Okay. When I'm writing this variable in the objective function, I'm putting 30x 3, 4, and then I put plus 30x 4, 3. And every one of these middle variables have to be written that way. So let's try to figure out how, where's the slide? How many variables will we end up with in the objective function? Here's everything coming from 1, 1, 2, 1, 3, 1, 4, 1, 5. They're one ways. You're only going to see those numbers with those once. Everything going into 6, 4, 6, 3, 6, 2, 6. That's it? Just 3 are going in? Oh, 1, 6. Thank you. 1, 6. You only see those once. But you go to things like 62, 5. I know there's a 65, 2. That's a 6. 33, 4, I know there's a 34, 3. There it is. 93, 5, there's 95, 3. For all of the middle ones, there's two variables, same number of cost, but it's two different directions. So you got to flip the numbers. So x 3, 5, x 5, 3. So that's how you determine how many variables there are total. So we wrote our objective function. We wrote all our constraints. Look at equals 1, equals 1, 0, 0, 0, 0. Here's number 5. 4 positives, 4 negatives, and it's just a coincidence, but the ones going in are negative here. But you could go, again, you could have made these all positive, the ones going in. Hey, I only see 3. 1, 2, 3. Well, that's no 4, that's why. 1, 2, 3, 4. You could have made all the ones going in all of these nodes positive, but then you've got to make sure you're consistent in the ones going out negative. Everybody understand how that is? You just got to have that consistency whichever direction you go. Now my question for you is, she's about to leave because you gave her route. And my question is, she's leaving node 1, where does she go first? Node 1. 3. How did you know that? Anybody see it? In shortest route, your optimal solutions only have 1s or 0s. And the 1s represent the route. So if you look at where the one is, where there's a number 1 in the variable, x13 has a 1 as the optimal value, that means that's the first part of the route. 1 to 3. Then from 3 to where? 4. There's 3 to 4 with a 1. From 4 to where? 5. There's 4 to 5 with a 1. And from 5 to 6 with a 1. There's the route. The absolute lowest we can get away with spending, getting this employee to the conference is how much money? That's right, $150. That's what it would look like if we did software output, kind of. Here's Excel. I put it all in there. I posted this. This is exactly the same setup that we've had all through chapter 4 and 3. But it's just a lot more variables. That's all. It's just a ton more variables. Notice at the end, equals 1 at the top, and all zeros. 1 and 1 zeros. These formulas we would see here are just like the formulas we've always had. It's the optimal solution times the value that's lined up with constraint 1, which would be row 6, row 16. This times this, plus this times this, plus this times this, all the way across. Same thing we've seen all the time, so nothing's changed. Right here, the subjective function formula is going to be the optimal solution times the objective function number. This times this, plus this times this, plus this times this, and all the way down. Just like always. Now, these formulas are not that hard if you analyze them and really understand them. So it's between 16 and 12. 12, 16, 12, 16, 12, 16, 12, 16. You multiply, added to each other. Let me grab the second one here. Again, the optimal solution is 16. Constraint 2 is row 7. 7 times 16, 7 times 16, 7 times 16, 7 times 16, all added together. Nothing's changed, it's just a ton of variables, so it looks like a different spreadsheet. It looks like it's harder, but it's not. Help me through this. Oh, wait. Let me go. I want you to help me through what to put in solver. I gotta get it out of there. Hang on. I want you to say to yourself, can you do solver without me? All right, here we go. First thing says, set objective. I got to put a cell location right there. What would that cell location be? F18. That's right. Very good. It's where the objective function is being calculated. Next, is this a max min or a value of? Min. By changing variable cells, what is it asking for? Or where is it? How's that?
Variable.
I almost heard. That's right. It would be where the optimal solutions are going to be placed, the cell locations. So I'm going to highlight from E16 to wherever these zeros end. It looks like it goes all the way to U16. So E16 to U16. Now the constraints. Now what I want to point out about these constraints is that every one of them are equal. So I can group them all together because they're the same sign. You know how you can put all the less than's together and all the greater than's? Well, I can put all these in one. All I got to do is tell it all of these cells are equal to all of wherever these right-hand sides are located, wherever those cells are. So here I go. Let me put add. Where's the left-hand side? From here all the way to there. So E22 to E27, I'll switch this to just an equal sign. The right side is from, what is that, V22 all the way to V27. Whoop, V27, right? 22, 27, 22, 27, equal sign. We're done with that. And can I solve? Oh, yeah, what? What do I have to do? Yeah, they can't be negative. What else? Is that it? We're good? Oh, simplex, yeah, okay, simplex. All right. Can I go now? There's one more thing, right? Good check. Whoop. My question for you is, how much, again, will it cost, minimal, to get the employee to the conference? Where is it at? Objective function value. What else? I guess that's it. Oh, the route. X13, from 3 to 4, 4 to 5, 5 to 6. Same hand. Okay? And that's posted. So you can have it ready to go for the quiz tomorrow. Monday, okay, good. Not Saturday? All right, ready? We're on our way. Max flow, maximal flow. The most common place I've known of this being used is municipalities. They use this concept, this network model, when they're trying to figure out if they can reroute the flow of traffic and enough traffic to do a project that's going to need a detour. And so this max flow is all about calculating all the different ways things could go, but they all have to meet up at the other end. And it's calculating how many total could get to the other end through all these different options. The example is a great example, by the way, because this is real. We're talking about this right here. Shipping companies, you ever drive by Flint Bishop Airport at night, the planes you're seeing that are just a little off to the right of the airport, if you're looking from the road, they're not carrying people, they're carrying packages. Every night, all these planes are going all over the place taking packages that people want delivered the next day. Businesses all over the world, the country, want them there as fast as possible. And these delivery companies take pride of getting the packages there the next day. So much so that they have plans in place, everything figured out in case a plane breaks down. For example, let me just jump to this. This is just one contingency plan. If in San Diego, out of the 4 planes, 1 breaks down, we still have the 3 other planes. Can we get, and then they go, okay, the average amount of packages, or the most we've ever had on the on any one plane coming from the city is, this is in thousands by the way, is like 8,000 cubic feet. So if that plane broke down, could we get 8,000 cubic feet from here, split it up with the planes that are working, and somehow get it to Tampa and have enough capacity in the network to get those 8,000 pounds there, even if that plane breaks down. And then you got to do it all again if, I got to think, man, we have Denver be number 1, and however many planes it has leaving at night, and which directions, and if one plane breaks down there, then the whole thing's calculated out again. And you do it again then from Houston. And so this is real. And this is exactly how it's done. And it's all, but most of the numbers are based on estimated averages based on the past. So I just got done saying that 8,000 is the most that's ever happened. We're trying to make sure that we have, that we have a plan in place that will get those 8,000 here. But who knows what's happening on a plane coming out of Denver? That could be 12,000. So we got to recalculate everything based on most average extra capacity. The plane that goes from San Diego to Houston, it usually has about 3,000 cubic square feet available of extra capacity it doesn't use, or even more. You got to be conservative with these estimates when you're doing this. So that would be the least they would have available. The plane going from San Diego to Dallas usually has 4,000 or more cubic square feet available that they're not using, and so on and so on. And these are all the possible extra capacities for each of these planes that there are some are going at the exact same time that's available if we need to get packages to the end. You keep switching where the destination is, you keep switching where the origin is, and you recalculate. You have plans for everybody, for every city, just in case, so they can still get the packages out. So now, you ready? Here's the rules you want to learn about this. First of all, every node is a constraint, is still valid. Every arc is available, a variable is still valid. Notice there's arrows on all these arcs. There's none of that assuming going both ways. You'll know which way they're going. Okay, here's what's different. The numbers on the arcs are not part of the objective function. This is the only one that's true. Max flow, the numbers on the arcs, are not part of the objective function. Number 2, every node constraint has both positive and negative variables. Every node, the beginning, the end, the middles, they all have positive and negative. None of these will have just positive or negative. Like in shortest route, how the beginning and end have just positive. It's not like that with max flow. They all have both positive and negative. Okay? What's the other thing I want to say is, in max flow, the node constraints are consistent with all the other ones, but in max flow, every arc with its number is an additional constraint. On top of these constraints, so you have the 7 node constraints, and then you're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 more constraints beyond these 7 node constraints, because every arc with a number on it is a constraint. Only in max flow is that the case. All right. Now, one more thing I want you to for sure write down. The very first step of max flow is to draw an arc to remind you from the end, whatever the biggest number node is, the end, back to the beginning, and put an arrow pointing at the beginning, as if that's a plane coming back or something, but it's not. Okay? When you draw that arc, you can then write your objective function. Because for max flow, the objective function is to max the variable of the arc you just wrote, that you just created. So in this case, the objective function would be max x 7, 1. Because the line we would have drawn would have been right here, back to there. There's the objective function. That's it. Nothing else in it but whatever the arc is you drew from the end, whatever that number is, to the beginning. Did I put 7, 1 or 1, 7? Yeah, the number in order from whatever the biggest number is to back to 1. That arc is not a constraint. There's no number on it. You created it. All the other arcs with the numbers on, they are constraints. Okay. Now I can go through and start writing constraints for all these nodes, but you've seen it 100 times. But I want to make sure you understand the rule about how they all have positive and negatives, even the beginning and end. So I'll do the node 1. Every one of these nodes, by the way, are equal. The constraints are equal to 0, just like they're all middle nodes. Just like shortest routes middle nodes are all equal to 0. These are all equal to 0. All right, so I'm doing node 1, and I see how many variables would there be in node 1 constraint. You want to say 3, but really there's how many? Really there's how many? Thank you for jumping into it. I really appreciate it. How many arcs are touching node 1 after we changed it slightly? Thank you. That's how many variables. What you're not visualizing is this arc that would touch there also. Those 3 plus that 1. 1's going into node 1, and 3 are heading out. So whatever this first constraint, whichever way you decide to make positive and negatives, you've got to be consistent for every node, including node 7, which is going to have both directions also, in and out. I'll go with, we went with negative going in last time, so I'll go negative going in again, I guess. So negative x 7, 1 plus x 1, 2 plus x 1, 4 plus x 1, 3 equals 0. There's node 1. So I want to make sure everybody gets this. I'll be with node 7. Start me out with the ones going into 7. What do I put? I'm sorry, what? Negative what?
X 5, 7.
Negative x 5, 7.
Minus X 4, 7.
Minus x 4, 7.
Minus X 6, 7.
Minus x 6, 7.
Plus X 7, 1.
Plus x 7, 1. Great catch there, Michael. Appreciate it. Then what else?
Equals 0.
Equals 0. The ones going into 7 to stay consistent with the ones going in are all negative. The ones leaving 7 are positive, and we made sure to include the arc that we drew. Okay. You can do all, do you want me to do, I'm just going to do 4 verbally just to make sure you're getting this. You ready? Negative x 1, 4, minus x 2, 4, minus x 5, 4, minus x 3, 4, minus x 6, 4, I got to stare, plus x x42 plus x45 plus x43 plus x46 plus x47 equals 0. Did I miss anything? I was just kind of going around. Okay, that's how easy these are. You could do all these. But this is the first time you're about to see a constraint from an arc. Let's go grab an arc there. Let's look at the one from 1, 2. You see the number 4 on it? Here's how you write the constraint. X 1, 2 less than equal to 4. Say whatever amount you're going to put on this plane going from San Diego to Denver cannot go over 4,000 cubic feet of space. And these variables are representing how many packages that you can put on each of these flights to then merge at the end to the most you can get through this system. That's what this is all trying to figure out. What's the most? Help me with the arc going from node 4 to 6. X. Anybody? 4, 6 is less than equal to 1. That's it. You're going to have 17 of those for every arc that has a number on it. And it looks like, yeah, hey, let's look at that. Right there. There's our objective function, just that arc we drew. Here's all the nodes, both negative and positive for every one of them. And then here's all the arc constraints. 17, is that what it's? I don't know how many, but a lot of extra constraints. And then you're telling me, can the 8,000, remember everything's in thousands, can the 8 cubic feet of packages that usually are on that plane that just broke down make it to through the whole system to the other end? Yes or no? How many could make it? 10,000. There's 2 places to find the answer. The arc you drew will always represent the most that could go from the end back to the beginning, which represents the most that can go through the system. And the objective function value represents the same thing. Now, I want you to visualize this. If a plane breaks down in San Diego, there's 3 planes heading out to these other cities. One's going to 2, one's going to 3, and somewhere else. How many cubic feet are going on the plane? Hang on a minute. You got to look at from the plane going from San Diego to Denver. Look at the route. Okay, now let me get the answer. I got to look. Okay, how many cubic are going on that plane? Huh? That's going on from route 1, 2. 3,000 or 3 out of the 8 are going on this route. Look at your PowerPoints. Tell me what 1 to 3 is from San Diego to where? The reason I'm having you look at that is because the question may say, here's the results. The plane going from San Diego to Houston is going to have how much of that 8,000? 3. And or could have up to 3, and the plane going to the 4th city could have to 4, which tells you right there the most that you can get out of that system. And it just so happens, when we get to the end, there's all 10. It actually calculated backwards, making sure everything can get through. So it's telling you, here's the most you can get on those 3 planes. When that plane arrives in, is that Houston, or is 3 Houston? 3 is Houston? When that plane arrives in Houston, is there any other planes arriving in Houston that also have some of the original packages? So the one going to Houston is 3. Is there any other planes arriving in Houston other than that first plane from San Diego with packages? 2 or 3. Very good. Right there. Some of them that went to 4 went here. Matter of fact, 4,000 could go to 4, and if so, 2,000 could go to Houston. But where's the other 2,000 going to go? Where do you see it? For what? Maybe I don't see it. Forget that question. Oh, right there. Right there. So there, right there. And 4, 7. So there's more. Oh, here's another 1,000 being dropped off. So 5 are being dropped off there. 2 heading here, and 3 heading there. That's to 7. You follow this along, you can see the logic behind the whole thing and how many could be sent to each city. And that's the thing we got to get used to, is how to interpret numbers like this to the question in words. hey, the plane broke down. How many is going to be on this flight from San Diego to Houston? And you're going to go, oh, that's X13, 3 could be on that plane, right? I'm not going to say what is the amount of packages that could be on route from 1 to 3. I'm going to use words that you're going to have to interpret, and the answer is going to be right there in front of you if you can interpret it. Any questions? Can we do a max flow? Let's do this. We were doing this before you guys got here because I got here early and I didn't think anyone was showing up. I think the key to this quiz you're about to take, Saturday? Okay, I can't remember. Is recognizing what kind of question you're looking at, from chapter 6 especially. So I'm just going to show you something from chapter 6 real quick on the screen. You tell me which of the 5 models it is. In case you need to refresh the memory, is transportation assignment, transshipment, shortest route, and max flow. Ready? Here we go. The bottom picture right there. What kind of model do you think this is? Transshipment. Stop. It's either shortest route or
Max flow.
max flow. Now it looks like a shortest route, but look at all these arrows. It's not a typical shortest route to have these arrows here, unless they're all just one ways for some weird thing. So there's a chance we have to read the problem, but we got it down to 2 models. This is either this is either shortest route or max flow. All right, hang on, let me grab another here. Right, this one right there.
Shortest route.
Could be shortest route, but with all these arrows, it leads me to believe it's most likely max flow.
It says the shortest route.
Find the shortest route. 23 may be looking at this picture over here, though. This could be 24, but maybe not. Is the picture usually under? Okay. Let's do the bottom one. That one's obvious. That one's so obvious. Look at how there's no arrows on the arcs between those nodes.
Shortest route.
Shortest route. That's why I jumped out of it. Again, I don't want you to see the page which way I'm going. That might give it away. Okay, number 10. Number 10. What kind of problem? I don't know the answer yet. Give me a second. Whoops. Okay, go ahead.
Transshipment.
Not transshipment. I would have thought transshipment too. Who said that? Was it? Who was it? Over here? Oh, I thought transshipment at first also, but I don't see the middle person. So instead it's what? Transportation. Now the reason it's not assignment, it should jump out at you that it's not just one thing being assigned to one thing. You can see all these numbers about demand in gallons. You wouldn't see all those 40 gallons and 50 gallons in an assignment problem. So you've got it down to either transportation, transshipment. Then it's a matter of reading it through to see if there's a middle. If something's going somewhere, then going somewhere else, you've got definitely transshipment. But I see, it looks like things are going from our suppliers 1 through 6 to our divisions who have demands 1 through 5, and here are the costs for each division if they happen to want to get it from any of these suppliers. And we want the orders to be ordered from the right suppliers to our right division to probably keep our costs as low as possible, because I believe these are probably representing costs for each unit order. Does that sound right? The cost per gallon, yeah, there you go. Want to try another? Want another? We got an in-class time. We still got time?
Are we sure that that's not assignment though?
Well, let's see. Is there a supply? Can the supplier only supply so much? Yeah, I think they're ordering units. But where's the supplies capacity? Oh, maybe the next page. Nope. I don't see the supply capacity. Well, what are these numbers then? This is price per gallon for the supplier. What are these? The cost per gallon for shipping. There's where the cost per gallon for shipping, which is what we're trying to minimize, which by the way, where would these numbers be? Constraints? Objective function? Objective function. All right. You'd have to read through the whole thing. God, I hate putting these up here without the drawings, because the drawings make it so easy, but the word is. Let me look at this real quick. This, no. We already did that one. They weren't here, but yeah, it's there. Okay. All right. Hang posted 5 example problems answers. And I looked at your book, the latest version of these, to make sure that these were the numbers, because some of these are old. And each one of these represents one of the 5 models. So, let's look at number 11. Here we go. You tell me, you look at number 11, it's one of the 5. Let me stare at it. Okay, got it. What is it? This is yours. This is yours. Ah, she beat me to it. Thank you. Thank you, Paige, for showing them up. It's transshipment. Now, this is why it's obvious, all right? It's going from the plant to a warehouse, but then it's going from a warehouse to a customer. Everybody see that? Going from the plant to the warehouse with its capacities, then it's going from the warehouse to its customer's demand. In the warehouse, everything that goes in, you have to back out. That's transshipment right there. Let's try this one. Again. How are we doing on time? We got time for this? We got time. I don't know how we got dinner. I better look at my notes. Number 29 at the top. What kind of problem do you think that is? You wrote that and took your tongue.
Max flow.
Max flow. Max flow. Entering, this is a traffic problem, just like a lot of municipalities do. Entering Albany, here's all the different routes when we set up the detours, how many can leave. What's that amount? They have those things all the time, all over the place. They know exactly how much traffic is going between this point and this point, and this point and this point. You guys know, you ever run over those little round tubes on the road? Those are counting cars. I know a lot of people think it does speed limit, and I don't know if they do or not, but really, the objective is to count. They need to know exactly how many cars. All the time, they need to know the average of the traffic, so when they plan, construction, highway and road construction problems projects are happening all the time. They constantly got to plan what the best detour route would be to get the flow through, even though a road might be closed.
So it's safe to assume that it affects an arrow on every line is max flow.
I proved it wrong. I mean, you got to read the problem too, but almost. But the reason this jumps out at me is because you got arrows coming in and arrows going out, and that kind of gave it away as a max flow, really. Before I read it, but you kind of got to read, because when you look at something like that, you know it's either shortest route or max flow. There's no way that could be assignment or, you know. Here we go. Let's do one more before we start the class. And I'm going right here. What's left, by the way? I know, remember, there's one of each, so you can kind of cancel these out. Well, I'm at the number 7 at the bottom of the page there. Wait, I got to stare at it. Wait, I don't know the answer. Wait, let me look. So just in case, let's go with this one. I got to remember that one. Here we go. Number 3 at the top of the page. Now, you almost have to read that first paragraph to really know for sure which one this is. It's giving you totals. Giving you, whoops, could you go darker, or is that just the screen? See? What kind of model? Say it. Say it. Just come right on your tongue. You just finish it. Portation. Oh, you were trying to say transshipment? Oh, darn. That's why. Oh, sorry, I talked to you. All right, it's transportation, because at the beginning paragraph it says there's 2 companies, Southern Gas and Northern Gas, and demand forecast for the coming winter: Hamilton County 400 units, Butler County 200 units, Claremont 300 units. The company can provide Southern Gas, there's 500 units available, and Northern Gas, there's 400 units available. There's all your supply and demand information, which leads you to go, okay, this is distribution, it's not assignment. Look at all these, there's far more than single units. And then this represents the cost for each unit being shipped, and that's what gives it away as transportation. Your left nodes would be Southern and Northern Gas, with a 500 and a 400 on the outside. Don't forget those numbers on the outside if you have to draw a network, and you might have to draw a network. On the right side are our 3 customers, and on outside of their nodes are the demand amounts, which are, what do we know? Is that 400? 400, 200, and 300, I guess. Yeah, I got, there's 900 available, it makes sense now. And then the arcs in between, can both north and south deliver to all three customers, or is there some delivery that can't be made?
They can all.
Huh?
They all.
All. Because you have numbers for every supply to every demand, that means any place can deliver to any place. If that 15, where it says southern gas to Claremont, was not there, it's trying to tell you that's not an option. Do not draw an arc from that node to that node. Do not put a number. It's not an option. Do not include it in your constraints. Okay? All right. Let's go to the in-class assignment. You guys have enough. It's an overkill now. Work together. Don't work alone. All right? You ready? You guys are all you're gonna help some people? Are you okay? All right, you ready? You ready? You're gonna work with them? Are you guys gonna work? Okay. Right from the start. I want you to help each other from the beginning. Don't attack this and not help people, you guys. Me? No? All right. Nobody's listening. Good luck. Good luck. Oh, time's up.